First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
All right, so today we're going to be looking at rate in, rate out FRQs. So this is a very conventional type of FRQ that you'll see on the AP Calculus exam. And typically the situation is they give you something of a rate going in, bananas on the table, people on the escalator, and then give you the rate for that particular thing going out. And we're going to look at the common type of questions that are asked on these type of problems. Bear in mind, we're just providing the foundation of how these type of problems are going to look. When you actually see the problem on the actual test, it's probably sure to have some type of nuance or novelty that you're going to have to deal with. And so, of course, it should have that, or else, the AP exam would be a tremendously easy test. So to make it challenging, you have to add some type of nuance or some type of novelty. And just your understanding of calculus, your understanding of trig and algebra and pre-calculus will dictate whether or not you're able to deal with that particular novelty or nuance effectively. So I have two example problems that we're going to look at. One is a calculator-based problem, and the other is a non-calculator problem. And as we go through these two examples, we'll kind of get a look at the type of situations you have to deal with on these rate in, rate out problems. All right, so here's my first example. This first example is a calculator-based problem. So we're going to do our calculations in the calculator. But of course, there's things we need to write on our paper. So we're going to write some things down, of course, but we're going to do the main calculations within the calculator. So let me go ahead and read the problem, and then we'll get to it. And so it says the rate at which snow accumulates at the top of a mountain during the winter is modeled by S of t, where S of t is measured in centimeters per hour and t is measured in hours since the first day of winter. Snow melts from the top of the mountain during the winter at a rate modeled by M of t, where M of t is measured in centimeters per hour and t is measured in hours since the first day of winter. There were already 7 centimeters of snow at the top of the mountain at the time t equals 0. And I say this all the time about AP Calculus problems, where there is no superfluous information given. So generally, all the information they give you is very relevant. And so when you're dealing with a rate in, rate out problem, they're pretty easy to recognize, because the problem is dealing with a rate in, and in this case, the amount of snow accumulating on the top of the mountain, and a rate out, in this case, the amount of snow melting on the top of the mountain. So they're pretty easy to recognize, and you want to recognize the rate in and the rate out. It's also important the units of measurement of the rate in and the rate out, because typically you're going to have to take the derivative of that particular function, and typically they want to know the units of measurement for the derivative, and you also want to know the units of measure for the independent variable, because that affects the units of measurement of the derivative of the rate. So basically, all of this information is important. Also, the fact that there is an initial value at time t equals 0. In this case, there are 7 centimeters of snow at time t equals 0. That information is very important. So really, when doing these problems, you really want to read through the problem all the way. Again, if there's some nuance, if there's some novelty, you have to really read the problem all the way through to make sure you get it. So no matter how good you may be, you don't want to be so arrogant where you just see, okay, I see the two functions, I know what to do. So please read through the information and digest it. You have time to read through the information fully and to tackle the problem. All right, so for this particular example, we have 4 different problems we're going to look at. Problems A, B, C, and D. And again, these are the typical problems that they ask, so you should be able to answer these type of questions and just be prepared for any type of nuance or novelty that they may add. So let's look at our problem A. So problem A says how many centimeters of snow melt from the top of the mountain during the first 4 hours of winter. So this is a typical question they typically ask you about an accumulation for one of the rates, whether it's the rate in or the rate out. And this particular question, they're asking me about the accumulation of the rate out because it's talking about the amount of snow that melts. All right, so this is a calculator-based problem. And so I'm going to define the two functions in the calculator. If I'm using a TI-84, I'm always going to make the rate in y1 and the rate out y2 because generally you have to recall the functions numerous times, and so you don't have to keep thinking, well, which function was the rate in, which one was the rate out. If I'm doing the Inspire or some other maybe more sophisticated type of calculator, I like to call the rate in F and the rate out G. So that's just kind of what I like to do to keep it consistent. So first I want to put these functions into the calculator. All right, so I'm gonna go ahead and type the functions in. So the rate in, that was S of t. I'm gonna call it F of t. Again, I could call it S of t if I wanted, but I just have this general scheme where I always call the rate in F and the rate out G. So that helps me remember when I'm recalling which one is which. And the rate out, which is M of t, which I'll call G. All right, so we have the two functions defined. And now let's go back to question A. And so question A was how many centimeters of snow melt from the top of the mountain during the first 4 hours? So the first 4 hours, of course, are from time t equals 0 to time t equals 4. So let's write what we're going to have to write on our paper. And so what we want to find is the integral from 0 to 4 of m of t dt. Really, it's that simple. Of course, we're going to find that actual answer using the calculator, but what we simply need to write is this, and then once we get the number, we'll of course put the number there. We don't have to write specifically what the function m of t is, just integrating the function m of t from 0 to 4 is sufficient. So let's go ahead and integrate on the calculator. All right, so we're going to integrate from 0 to 4, the rate out, and my rate out was G. So we're going to integrate G of t from 0 to 4, so G of t dt. All right, so we get 1.67 if we round it. So normally, if they don't tell you how to round, which in a lot of problems they don't, the general rule is we're going to round to 3 decimal places. So this one is going to round to 1.67. All right, so 1.67, and that problem is done. So all they were asked us for this number, they're not asked us to explain the meaning or anything like that, because actually they're telling we know the meaning. The meaning is the amount of snow that melted during the first 4 hours, or they're not asking us for units of measurement or anything. So we're only going to give them what they asked for. What I like to do once I find the answer and we found the answer, I just like to go back to the question just to make sure I answered everything they're asking. Sometimes they may have asked for something and maybe I didn't pay attention and missed it. So before I move on to the next problem, I just like to go back and look at the answer, look at the question to make sure I answered everything they were asking. All right, so going back to the question, it just says how many centimeters of snow melt from the top of the mountain during the first 4 hours. We have sufficiently answered that question. Let's look at the next problem. This is problem B. Problem B says find S prime of 6 using correct units. Explain the meaning of S prime of 6 in the context of the problem. All right, so this was A. So now we're doing B. So as far as what we need to write S prime of 6. and then we'll write what it equals, and then we'll explain what it means in the context of the problem. So let's figure out what S prime of 6 is. And so S was the rate in, and so I like to call the rate in F. So we're going to find F prime of 6. So we're going to take the derivative with respect to t of F of t. When t when t is 6. All right, so that's 1.611 when we round it. So this is 1.611. Now it says explain the meaning of this, and it says something about using the correct units. So this is how I like to do this. So basically we're taking a derivative. You know, the function was already a rate. S of t was already a rate. We're taking a derivative. This is how I like to write up the explanation of what these represent in context of the problem. So anytime they're asking me to explain what the derivative represents, and I'm taking the derivative of a rate, I like to start off the sentence by saying the rate at which the rate. So that's always going to be my opening statement, the rate at which the rate. And then after that, I'm going to put in what the rate represents in the problem. So what the problem is saying the rate represents. So this is S of t. If we go back, what S of t represents. So excuse me, if we go back to what S of t represents, it's the rate at which snow accumulates at the top of the mountain during the winter. So I'm just going to say the rate at which snow accumulates at the top of the mountain. I think I can leave off during the winter and be okay. So S of t represents the rate at which snow accumulates at the top of the mountain. So to continue my statement, the rate at which the rate of snow accumulates at the top of the mountain pardon my handwriting. I definitely need some help, but you know, we'll live with it. So again, let's go over how we write this up. So we begin with the rate at which the rate, then we insert what the rate represents. So the rate at which the rate of snow accumulates at the top of the mountain. After that, we should follow with the statement increases or decreases. And that's dependent upon if the derivative was positive or negative. If it's positive, we're going to say increases. If it's negative, we're going to say decreases. Obviously, in this particular problem, it was positive 1.611, so we're going to say increases. So the rate at which the rate of snow accumulates at the top of the mountain increases. Wow, increases by 1.611. And this, once we enter in that amount, this is where we're entering the units of measure. So remember, the units for S of t were centimeters per hour. The units of S of t were centimeters per hour. When we take its derivative, it's going to give the units of S per the units of the independent variable t. The units of t were hours. So the units of S prime of t are going to be centimeters per hour per hour. Or we can also, of course, just write centimeters per hour squared. So when you take a derivative of a function, the units of the derivative are going to be the units of the function per the units of the independent variable. So the rate at which the rate of snow accumulates at the top of the mountain increases by 1.611 centimeters per hour per hour. And then the last part you need to this, because the derivative is at a particular moment. And so this measurement represents something going on at a particular moment, and you want to say what that moment is. So at time t equals 6. So that's an easy way to write up these type of explanations that should get you your full amount of points. Again, you're taking the derivative of a rate. So you start off with the rate at which the rate, and then you explain what the rate is of snow accumulates at the top of the mountain, and then you say if it's increasing or decreasing depending on the value of the derivative. In this case, it increases by 1.611. And then, of course, you put in the units of measurements, which are the units of the original function per the units of the independent variable. So centimeters per hour. And lastly, you put at the moment this is occurring, and this is occurring at time t equals 6. So if you kind of can remember the general structure of that answer, you should get all the points for this particular problem. Okay, let's look at the next problem. All right, problem C. So it asks, is the amount of snow at the top of the mountain increasing or decreasing at time t equals 1? Give a reason for your answer. So how do we tell if a function is increasing or decreasing in calculus? It depends on if the derivative is greater than 0 or less than 0. That's how we tell if a function is increasing. So if your derivative is greater than 0, the original function is increasing. If the derivative is less than 0, the original function is decreasing at that particular moment. So we're talking about, is the amount of snow increasing or decreasing? So we're not talking about is the rate of which snow accumulates increasing or decreasing. We're talking about is the amount of snow increasing or decreasing. So that means our two functions, s of t and m of t, they represent the derivative of the amounts because they're rates. And this is talking about is the amount increasing or decreasing. So for this particular problem, we actually don't have to take the derivative of s and m. We just need to evaluate s of 1 minus m of 1 because they're going to represent the derivatives of the amount of snow because, again, those two functions are rates. So a common mistake on this would be to take the derivative, but you have to read the question carefully. It's saying, is the amount of snow increasing or decreasing? So to determine that, you need to see if the rate of snow is increasing or decreasing at time t equals 1. And the rates, again, are given by s of t and m of t. And since it just says is the amount of snow, period, so we have to look at the rate of snow accumulating minus the rate of snow melting. So again, that's simply s of 1 minus m of 1. If that value is negative, then we're going to say it's decreasing. If that value is positive, then we're going to say it's increasing. That's our rationale. So let's look at what s of 1 minus m of 1 actually equals. All right, so again, s was f. So f of 1 minus my m was g minus g of 1, and that's going to equal 6.847. 6.847. So s of 1 minus m of 1 is 6.847. So therefore, or we can say the amount of snow the amount of snow is increasing at time t equals 1 because, And the reason this increases is because S of 1 minus M of 1 is greater than 0. So because S of 1 minus M of 1 is greater than 0. So this is the rationale. You do want to put what the value of S of 1 minus M of 1 equaled, and you do want to show you're actually calculating S of 1 minus M of 1. But if you show you're calculating S of 1 minus M of 1, and you say whether the amount is increasing or decreasing, that's of course based on the fact if that value was positive or negative. So it's really all you need on that one. You see, pretty easy. So let's look at our last problem for this particular example. So the last question we have here, and this is like the big question. So how many centimeters of snow are at the top of the mountain at time t equals 2? So it's not just asking how much snow melted or how much snow accumulated. It's asking how much snow period is at the top of the mountain at time equals 2. So to be able to find that, we have to look at the amount of snow that accumulated at time t equals 2. That would be integrating S of t from 0 to 2. But we also have to subtract the amount of snow that melted at time t equals 2. So we're going to have to subtract the integral of M of t from 0 to 2. But also we have to take into consideration the amount of snow that was already there at time t equals 0, which was 7 centimeters. So we're going to have to add the 7 centimeters to the mix. So the setup is going to look something like this. So this is letter D. So we're going to have the integral from 0 to 2 of S of t, and that's going to tell us the amount of snow that accumulated, minus the integral from 0 to 2 of M of t. So that's going to subtract the amount of snow that melted, plus 7, plus the amount of snow that was there from the very beginning. So go ahead and find this number. All right, so we're going to integrate from 0 to 2. First, F, what I've put in as F, which of course is S of t. And that's going from 0 to 2. And then I'm going to subtract, and then I'm going to subtract the integral from 0 to 2 of G of t. And then plus 7. All right, so 17.717, 17.717. So how do we write this? We write equals 17.717. That's all they're asking for. And then asking us to put units of measurement. I mean, they're in the problem, it's telling us units of measurement. The units of measurement is centimeters, of course, but they're not asking for that. And so we only want to put exactly everything that they're asking for. All right, so that's our first rate in, rate out problem. And this was a calculator problem. We're going to look at a non-calculator problem in our part 2 video. So our part 2 video will look at another example of a rate in, rate out problem. This one will be a non-calculator problem, but many of the questions will be the same. And again, in these questions, we're just illustrating, the conventional way these problems are asked. But again, when you see the actual problem, you should expect some type of nuance or novelty to make your problem a little more challenging. We'll see you next time.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.